Okay. If theorem is, if f is a mapping from A to R is uniformly continuous, on a subset A of R, and if xn is a Cauchy sequence, in A, then f of xn, this sequence is a Cauchy sequence in R. It means if f is a uniformly continuous function, then it will transfer the Cauchy sequence to the Cauchy sequence. The proof is simple. Let xn be a Cauchy sequence. In A. Okay. We wanted to, and f is given to be, and f is given to be uniform continuous over A. So, by definition of the continuity, let for a given f signal greater than 0, we can identify a delta. There exists a delta which depends only on f signal greater than 0, such that the mod x minus u is less than delta, such that for if x comma y, x comma u belongs to A, satisfy this condition, then f of x minus f of u, this is less than f signal. Okay. So, let it be 1. Now, it is given the sequence xn is a Cauchy sequence. So, since xn is a Cauchy sequence, so by definition of Cauchy, so for a given f signal greater than 0, for given delta, we can say there exists for given delta greater than 0, there exists an h which depends on delta, such that the difference between any two arbitrary term of the sequence after a certain stage can be made less than delta for all mn which are greater than or equal to h. This is 2. Okay. Now, by this same delta, if by the same choice of delta, since xmn is less than this, so if you take x equal to xn, u equal to xn, so from 1 it follows that f of xn minus f of xm, minus f of xn, mod of this will be less than f signal for all nm greater than or equal to h. This shows the sequence f x n is a Cauchy sequence in R. So, that is proved the result for. Okay. Now, we come to the thing which is say our absolute continuity. That is a new absolute continuity. Absolute continuity means a function f x is said to be absolutely continuous in the interval say a b if corresponding to an arbitrarily chosen positive, arbitrary choosing positive number epsilon, another positive number delta can be assigned, can be determined such that for a sequence of non-overlapping interval, for a sequence of non-overlapping intervals H R K R, open interval H R K R, defined in A B, the sigma of mod f of H R minus f of K R is less than epsilon provided sigma of K R minus H R, this length is less than delta. So, what is here? It means that is, we can say, so we say the effect, that is f x is absolutely continuous function. The meaning of this is absolute continuous over the interval a b, if corresponding to a given epsilon, a number delta exists, such that in a countable set of non-overlapping intervals, of total length, I am not using the measure, of total length less than delta, the sum of the fluctuations of the function is less than epsilon, So, let us see what is the meaning of this is. Suppose we have a interval a b and a function f is given. We say this function is absolutely continuous in the interval a b if b for a given epsilon greater than 0. If we have a non-overlapping intervals, means divide this one, say in this non-overlapping, say here this is like this. If I take this non-overlapping intervals and so on like this. So, if we take a countable number of non-overlapping interval of this whose length is less than delta. So, we have to take a small portion, suppose I take this small portion, this. Now, this small portion is total length is delta, total length of this is delta. So, this small length we can over this small interval we can find a non-overlapping intervals such that sigma of this length k r minus h r, this length is less than delta. These are countable. 1 to infinity, r is 1 to infinity. Total length is less than delta. So, for a given f signal, say this f signal is there. For this given f signal, we can find a delta such that whenever we have a non-overlapping intervals, countable number of non-overlapping intervals whose length is less than delta, then corresponding fluctuation over these sub-intervals, the total sum of this corresponding this fluctuation should not exceed by f signal. If so, then we say that is sigma of mod f of hr minus f of kr. This should be less than f signal 1 to infinity. So, if the total fluctuation of the function over this sub intervals is less than f signal whenever the points are in this intervals in countable number of intervals whose length total sum is less than f delta, then function is said to be an absolutely continuous function. So, obviously, every absolutely continuous function is continuous. As a note, we can say function which is absolutely continuous in the interval a b is also continuous in accordance with Cauchy definition. Because what we do, we replace it, the total set Kr we consider of single interval. We can, the sum of these we can replace by a small interval, total sum is less than delta, and then correspondingly here we get the total fluctuation is less than f signal. So, this will be obviously true, consist of this, okay, less than then the condition of uniform continuity. Similarly, we can also say that we may take the same interval, single interval length delta, and definition of uniform continuity is also satisfied over this. Uniform continuity is also satisfied. So, function which is absolutely continuous is a continuous one, and for B also we say it is uniformly continuous. And in uniform continuity condition is also satisfied if we choose the Kr to consist of single interval of length delta. Okay. Converse is not true. That is, a function which is continuous may not be absolutely continuous in that interval. That is, a function which is continuous in the interval a b may not be absolutely okay, absolute TLY absolutely continuous in that interval. Okay. A function which is continuous may not be absolutely continuous. For example, if we take the function f x, which is defined as x sin 1 by x when x is different from 0 and 0 when x is 0. We know this function is a continuous function. This is a continuous. This we have seen, this function f x is continuous. This we have already seen. So, nothing, because the limit of this f x, because the limit of f x continuous at 0, okay, continuous at 0, and otherwise also is continuous in the total limit as x tends to 0 is the value of this function is coming to 0, which is f 0, and for other point at x belongs to 0 1 interval. In fact, entire interval it is continuous. because at the point 0 the value is coming to be this and continuity follows. Okay. Now, it is not absolutely continuous we claim, but this function f x is not absolutely continuous on the interval 0 1. Why? It means the condition of the absolute condition is not satisfied. That is, if we choose the infinite number or countable number of subintervals whose total length is less than delta, but the fluctuation may not be less than epsilon. So, that is what. So, suppose I divide the interval 0 1 in each of these subintervals, we get into subintervals say 1 by r pi 1 over r plus 1 pi, these subintervals where r is 1, 2, 3 and so on into subintervals and in each intervals in the subintervals 1 upon r pi and 1 upon r plus 1 by r is 1 to 3. The fluctuation of the function, f x, which is x sin 1 by x exceed by this number 1 by r plus 1 pi. Let us see why. Over this function, the region is over this function, this is our interval 1 by r pi, this is our interval 1 by r plus 1 pi. The function x sin 1 by x, if we look the function f x, which is x sin 1 by x, at the end point the sign of this is 0, because it is an integral multiple of pi. So, basically the function will go like this, because at this end point r pi or r plus 1 pi, this value will give the value 0. So, the fluctuation of the function, the value of this minus the value of this will be something which is greater than this number. Now, here the maximum value, suppose I take x equal to say let us choose x to be 2 over 1 by x to be 2 r plus 1 pi by 2. Okay, 2 r plus 1 pi. So, x will be 1 upon this lying say here. Then what will be the sign of this value? Sign of 1 by x is 1, because odd multiple of this 1, and this value will give the f of x 2 r plus 1 pi by 2. The 1 upon 2 r plus 1 pi by 2. So, this will be greater than the value at this point r plus 1. So, fluctuation will be exceed by this number, which is greater than this, okay, by this. Clear? So, we get from here is that the fluctuation is exceeding by this. Therefore, the sum of the fluctuation. So, sum of the fluctuation in the sequence of intervals, say 1 by r pi, then 1 over r plus 1 pi, this sequence of intervals corresponding to r is equal to n, n plus 1 and so on, is greater than if I take the sum is greater than 1 by pi 1 over n plus 1, 1 over n plus 2 and so on. But this series is a diverging series. So, this cannot be made as small as we please, greater than. So, it is greater than by any assigned positive number a. Therefore, for the series. Therefore, this large number cannot be, so it is not a. So, the function f x, which is x sin 1 by x, x is different from 0 and 0 when x 0 is not absolutely continuous, absolute continuous. Okay. So, this one. Their results are just state the one result. The result says the sum and the product of two absolutely continuous functions are absolutely continuous, So, this proof follows on by the definition, and one can go with the proof. Thank you very much.